In this video, we will explore protection mechanisms, focusing on access control and capability-based systems. These mechanisms are crucial for ensuring the security and integrity of computer systems by managing how resources are accessed and used. Let's discuss why protection is needed in computer systems. The goals of protection mechanisms are to prevent unauthorized access to resources, ensuring that only legitimate users and processes can access sensitive data and system functionalities. Protection isolates processes from one another, preventing interference or malicious actions from one process affecting others. It also enforces sharing policies between users, dictating how resources can be shared and accessed among different users, maintaining fairness and security. Finally, protection safeguards system integrity from malicious or erroneous programs, ensuring that the system remains stable and reliable. Now, let's understand the concept of protection domains. A protection domain defines the set of resources a process can access. This is determined by the access rights that the process has to various objects within the system. A process's protection domain can change during its execution, allowing for dynamic adjustment of privileges as needed. Protection domains form the basis for privilege separation in operating systems, ensuring that processes operate with the minimum necessary privileges to perform their tasks. Let's explore the access control matrix, a conceptual model for implementing protection mechanisms. The access control matrix specifies the rights that each subject, such as a user or process, possesses for each object, such as a file or resource, in the system. In this matrix, subjects are listed in rows, and objects are listed in columns. Each cell at the intersection of a row and a column defines the access rights that the subject has for that particular object. For example, user 1 may have read and write access to file 1, read access to file 2, and print access to printer 1. User 2 may have read access to file 1, read, write, and own access to file 2. Process A may have read access to file 1 and print access to printer 1. The administrator might have read, write, and own access to both file 1 and file 2, print and manage access to printer 1, and execute and kill access to process A. Let's explore how access control is implemented in practice, focusing on access control lists and capability lists. Access control lists, or ACLs, are a column-based implementation of the access matrix, associating each object with a list of subjects and their corresponding access rights. For example, in Unix-like systems, file permissions are defined using ACLs. The file document.txt has an owner, user 1, with read, write, and execute permissions. The group developers has read and execute permissions, while others have only read permissions. Capability lists, on the other hand, are a row-based implementation of the access matrix, where each subject possesses a list of capabilities or tokens, granting them access to specific objects. User 1, for instance, has capabilities for document.txt, allowing read, write, and execute access, config.ini, allowing read access, and printer01, allowing print access. Let's take a closer look at the access control list structure. Access control lists associate a list of permissions with each object in the system. Each file has an ACL header with a list of users and their associated permissions. File 1 has an ACL header with entries for user 1, with read and write permissions, and user 2 with read permission. File 2 has an ACL header with entries for user 1, with read permissions, and user 2 with read and write permissions. Printer 1 has an ACL header with entries for user 1, with print permission, and admin with manage permissions. Some of the key characteristics of a CLS are that they are object-centric, efficient for checking access, and used in most file systems. However, it's difficult to determine all permissions for a user. Let's explore capability-based systems. Capabilities are unforgeable tokens that grant the possessor specific access rights to an object. Each user has a C-list header which associates them with various resources they can access. User 1's C-list header shows they can access file 1 with read and write permissions and printer 1 with print permissions. User 2's C-list header allows them to access file 1 with read permission and File 2 with read and write permissions. Process A's CList header allows them to access File 1 with read permission and Printer 1 with print permissions. User 1 has access to File 1 and Printer 1. User 2 has access to File 1 and File 2. Process A has access to File 1 and Printer 1. Let's examine the implementation of capabilities in more detail. The structure of a capability typically includes an object identifier, which is a unique identifier for the resource being accessed, access rights, represented as a bit vector indicating the specific permissions granted, and a random key, which serves as an unforgeable token to prevent unauthorized duplication or modification of the capability. Capabilities must be unforgeable, ensuring that they cannot be created or altered by unauthorized entities. They are protected by hardware or cryptography to maintain their integrity. Capabilities can be passed between processes, enabling controlled sharing of resources and privileges. Capabilities offer several key advantages, including efficient checking of permissions, the support of the principle of least privilege, enabling fine-grained access control, simplifying permission delegation, reducing vulnerability to confused deputy attacks, and widespread use in microkernels and distributed systems. Let's compare access control lists and capability-based systems across several key aspects. In terms of implementation, ACLs are associated with objects, such as files and resources, while capabilities are associated with subjects, such as users and processes. For permission checks, ACLs require searching the list for the subject's permissions, whereas capabilities allow for a direct check of the capability token. Revocation is easy with ACLs. Simply modify the object's ACL. However, with capabilities, it is more difficult as all copies of the capability must be found and removed. Delegation is complex with ACLs requiring ACL modification, but it is simple with capabilities. Simply pass the capability to another subject. Listing access is easy with ACLs. Listing all subjects with access to an object is straightforward, but it's difficult with capabilities to determine which subjects have access. Real-world examples of ACLs are Unix file permissions and Windows NTFS. Capability-based systems include KeyKOS, EROS, and SEL4 microkernel. Let's explore role-based access control, or RBAC, another approach to protection mechanisms. RBAC operates on several key principles. Permissions are assigned to roles rather than directly to users, simplifying management and ensuring consistency. Users are then assigned to appropriate roles based on their responsibilities and functions within the system. By assigning users to roles, they acquire the permissions associated with those roles, streamlining the granting of privileges. RBAC simplifies administration for large systems, making it easier to manage user permissions at scale. It also supports the principle of least privilege by ensuring that users only have the permissions necessary to perform their tasks. To illustrate RBAC implementation, consider a role definition for a developer. The developer role has permissions such as read source code, write source code, and run tests. To assign a user to this role, the system can use a function like user.assignRole, specifying the user Alice and the role developer. This assignment grants Alice the permissions associated with the developer role. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.